Back. Today we're going to go ahead and talk about controllability. Okay, so we're going to do three main things. So first we're going to define what controllability actually is. Following this, we're going to give some conditions for controllability for LTI systems. In particular, we'll talk about the Grommian and controllability matrix approaches. And then following this, we'll go ahead and talk about the controllability decomposition for linear systems. Okay, fantastic. So let's get right into it and start talking about what controllability actually is. So controllability and reachability. Okay, so I kind of want to start by, I don't know, maybe setting the stage a little bit for where we currently are in our class. Okay, so far in the course, everything that we've done is kind of just basic systems analysis, right? Like we studied some basic conditions for the stability of systems, we studied the kind of basic structure of solutions and all these sorts of things, right? So far we haven't really done any control, right? So this is the kind of turning point in the course where we go from more systems analysis to more control design and control analysis techniques, okay? So this is kind of an exciting time for us in the class. Okay, so with that kind of said, let's go ahead and let's, I don't know, maybe sketch out some of the basic ideas of controllability and reachability. Okay, and I basically want to kind of motivate these ideas first, just with a little scenario. Okay, so let's say, suppose I don't know, someone, maybe your PhD advisor or your boss or some such thing. Suppose they give you some specifications that you want your control system to meet, right? So let's say, I don't know, your boss comes up and he says, hey, this is my model for an airplane. I want you to design a controller for it to do this, okay? But there's this really fundamental idea, and that is you can't expect a system to do anything you want, right? Like deep down, there's going to be some fundamental limitations on performance for these different control systems, okay? So something that we'll kind of see today is that fundamental limitations on performance exist, okay? What's more, these fundamental limitations kind of inform how successfully we're going to be able to solve various control design problems, okay? So I'm just going to go ahead and sketch out some very basic examples for what I mean by this. So let's say, example one, let's say I want to stabilize my control system, okay? And let's say, someone goes ahead and they give you the kind of basic dynamics. X dot equals 1, 0, 0, 1 times x plus 1, 0 times u. All right? Now I just want you to take a moment and kind of think about this question, which is, can you stabilize the system? Okay, so just take a moment, give it some thought, and see what you kind of come up with. Okay. All right, so I'll assume that you've given this some basic thought, and the answer that maybe you arrived at is no, right? So we only have your input appearing in your kind of x1 component of the system, right? So I only have an input u appearing up here. Now the second component of my system is entirely decoupled from the input, right? x2 doesn't actually see any form of input, okay? So x2 does not see the input u. And this kind of lands us up at the basic problem where, maybe we could stabilize component x1 of our system, but x2 is unstable and it's completely uncontrollable, okay? So it is unstable and uncontrollable. What this kind of means is that really, no matter how clever we are with our control design for our system, there's nothing that we could do to stabilize this system, okay? So I can, kind of pull any number of nice control design tricks. Nothing is going to get me to stabilize this system, all right? So this kind of leads us to this idea that there exists fundamental limits on what control systems can actually do. All right, so this is going to be the theme for today's lecture. So basically what we're going to do when we discuss controllability and reachability is we're going to say, okay, here's a really nice wide class of problems that we'd like to be able to solve. Okay, these are problems that come up a lot. And what we're going to do is we're going to kind of try to figure out some basic characterizations of, when these kind of nice properties are able to be met, right? So for example, maybe I'm interested in doing stabilization, right? What class of linear systems is actually stabilizable, right? This is one of the questions we're going to be interested in answering. Okay, so with that said, let's kind of jump more into what controllability and reachability actually are, okay? So, just a couple moments ago, I said what we're going to do is we're going to set out a basic class of control objectives and then kind of try to characterize systems that are able to meet those, okay? So our general objective is to take the state of our system from one state and one time to another, okay? So we're going to start off at some state in time, and then we kind of want to get to another state at another given time, all right? So let's say maybe I'm designing, I don't know, like a robot system, right? Let's say I start at this state. This is x0. This is at time t0. Then I want to get to another state, x1 at time t1, okay? So if I'm able to kind of draw a path between those, then that means that, I have kind of good control authority over my system, okay? And this is really the fundamental idea of controllability. So the basic idea of controllability is that we can move our system between any pair of states for a given set of times. Okay? All right, so with this kind of basic notion in mind of controllability, or as I've abbreviated it here, CTRB, being this idea where we can go from one state at one time to any other state we want at any other time, we can kind of start to put down some more basic mathematical reasoning to these things, right? So what are some basic mathematical elements that we have over here? So the basic elements is we have a pair of a state and a time, right? So that's the main thing that we have. And then we're able to get from one pair to another. Okay, so these are the two basic pieces. So what I'm going to do now is I'm going to go ahead and use this kind of abstract dynamical system language that we developed much earlier in the course, and I'm going to put down two kind of mathematical definitions that correspond to these two components. Okay, so this gives us to our first definition, which is an event and a reachable event. Reachable event. Okay, nice. What I'll say is consider an I/O dynamical system, right? This is one of our abstract systems that we talked about all the way in lecture 1, right? And you might remember this is a system D, which is composed of an input signal space, an output signal space, a state transition map, which kind of tells us our dynamics, right? And then a readout map, which tells us how we make measurements, okay? And I'm also going to say that this system has a time set t, okay? Time set t, all right? So remember, t is some subset of the reals that satisfies some nice sort of conditions for us. Okay, so let's go ahead and first define an event. So an event for this system is just going to be a pair of a state and a time, okay? So an event is a pair of a state and time, okay? So this is going to be something like x comma t, where this belongs to, my state space sigma across with my time set t, all right? So if we kind of go ahead and look at this basic motivational example up here, what we have is we're saying, our system's basically going to be controllable if I can go from one event to another event, right? So let's kind of set the stage for that mathematically. So I'm going to say next what a reachable event is. So a reachable event. Okay, fantastic. So what I'm going to say is, let's consider two sort of events over here. Okay, so consider the events x0, t0, and x1, comma, t1. So what I'm going to say is that x1, comma, t1 is reachable from x0, t0 if there exists an input signal that transfers me from one to the other. Okay? All right. So I'll say that x1, comma, t1 is reachable from x0, comma, t0 if there exists an input signal u belonging to my input signal space such that phi of t1, t0, x0, u is going to equal x1. Okay? So I declare this event x1, comma, t1 to be reachable from my original event x0, t0 if there exists some input signal u that delivers me from x0, t0 to x1, t1. Okay? So we introduce some kind of nice notation to go along with this, which is if x1, comma, t1 is reachable from x0, comma, t0, we write the notation x0, comma, t0, this little squiggle arrow goes until x1, comma, t1. Okay? So this is a nice notation just to indicate that x1, t1 can in fact be reached from x0, t0. All right? So just note this arrow essentially says, okay, there exists an input signal u that transfers me from one to the other. Okay? It doesn't say anything about uniqueness. It just says there's some input out there that gets the job done. Okay, fantastic. So within the scope of this basic example, right, if we kind of have this scenario over here where we're able to draw a state trajectory from x0, t0 to x1, t1, here we have that x1, t1 is going to be an event that's reachable from x0, t0, right? Okay. So the basic idea of controllability is, if I'm given any pair of times, t0 and t1, I'm going to declare my system to be controllable if I can reach any final state from any initial state. Okay? So that leads us to the definition of controllability. So, oops, I'm still writing with the highlighter. Sure. So this is going to be one of our key definitions for today. This is controllability, which, as I mentioned earlier, I'll often just abbreviate as CTRB, okay, because this is kind of easier. So what I'll do is I'll say a dynamical system D equals U, Y, sigma, phi, R is controllable on an interval t0, comma, t1, which is a subset of t, if for all states x0, comma, x1, and sigma, I'm able to reach x1, comma, t1 from x0, comma, t0. Okay? So I have x0, t0. I'm able to reach x1, comma, t1. All right? So basically, I declare a system to be controllable if I can always reach any state from any initial state for these given times t0 and t1. Okay, so let me talk about some basic properties of this definition. Okay? So first, controllability at least appears to be dependent on the interval t0, comma, t1 for a general dynamical system. Okay? So something that we'll find kind of later in this lecture is that for the case of a linear dynamical system, controllability won't actually depend on what this interval is. Okay? So what else do we have? Well, second, what we have is that controllability really only depends on the state behavior. Okay? So controllability is almost entirely a property of state, right? So it's determined by how my state transition map interacts with these initial and final states and interacts with input signals, okay? So there's no presence of outputs. All right? This is going to be kind of important for us. Okay, fantastic. So what are we going to do with this kind of very basic abstract definition of controllability? Well, something that you might remember from much earlier in the class is we said, okay, it's great that we can make these very general abstract definitions, but oftentimes abstraction comes at a price, right? Whenever we make something that's super abstract, there's really not so much that's interesting that we can say about it, okay? So in order to actually say something interesting or useful about controllability, what we're going to do is we're going to add more structure to these dynamical systems. So this is going to be our next step. So next, what we'll do is we'll add more structure and examine controllability. Okay? All right. So what are some basic structures we can add to our system? Well, some basic things are linearity and time invariance, right? And, you might remember all the way in lecture 1, we kind of went ahead and we discussed these concepts for an input-output system, right? But previously what we did is we just said, this I/O map of our system, which is the composition of the readout map and the state transition map, is the map that needs to be linear and time invariant, right? But in the case of controllability, we're not really interested in this I/O behavior, right? We're only actually interested in the state behavior. So what I'm going to do now is I'm going to define what it means for the actual state transition map to be linear and to be time invariant, okay? All right. So that brings me to the following definition, which is linear time invariant state transition map. Okay, so what I'll say is consider a linear dynamical system, which is one of these I/O systems, right? D equals U, Y, sigma, phi, and R. So you might remember some basic conditions for this is we need the I/O map to have a linear structure, right? And we need each of these spaces, U, Y, and sigma, to be vector spaces, okay? So I'll say let this be on a time set T. And one condition of these vector spaces is that U, Y, and sigma need to have the same field, right? The same sort of scalars, okay? So I'll say that the field needs to be K, which is going to be either R or C, okay? All right, fantastic. So what I'm going to do is I'm now going to impose a couple of different conditions on the state transition map, okay? So we say that the state transition map is, first, linear if it is linear in sigma cross U. Okay? So what this is basically going to mean is that we're going to have phi of T1, T naught, alpha times x naught plus beta times x naught hat, comma, alpha U plus beta U hat equals alpha phi of T1, T naught, x naught, U plus beta of T1, T naught, x naught hat, U hat. Okay? So basically all that we're doing over here is we're just replacing where the I/O map would ordinarily be with our state transition map. Okay? So just as a quick side note, an equivalent way of writing this is that it's going to be an linear I/O system with readout map R sigma of Txu just equal to x, okay? So you can imagine that, alternatively, if I wanted to kind of write this out using what we had said already, I'm just going to declare that, if we pretend that the output of our system is our full state, then it needs to be a linear input-output system, okay? Now we can kind of do the same thing for time invariance, okay? So it's going to be time invariant if each of U and Y is delay invariant, right? So that means that if I shift any of the signals in U or Y, they kind of remain in those sets U and Y. And the state transition map phi is delay invariant, okay? So you might remember this means that phi of t1 plus tau, t naught plus tau, x naught, then the delayed version of my input signal is going to equal phi of t1, t naught, x naught, and then u, okay? Remember that t tau of u, evaluated at time t, is just equal to u of t minus tau, okay? So this just says that my state transition map needs to kind of stay the same under these different delays, all right? Now, once again, you could check this kind of equivalent condition up here, which just says, okay, now if we pretend the output of our system is just going to be the full state vector, then, we should have a linear time invariant I/O system, okay? All right, so just as a quick final remark, LTI phi means linear and time invariant phi. Okay, fantastic. So what we've done is we've now kind of given this state transition map an appropriate linear structure, right? We've also defined what it means for this thing to be time invariant. So now that we've done this, we can go ahead and kind of examine what the consequences are for controllability, all right? So let's go ahead and state this as a proposition. So proposition, this is going to be reachability and controllability of LTI systems. Okay, great. So I'll say consider a linear system D with linear state transition map phi. Okay? So first what I'm going to say is I'm going to declare some sort of condition about linearity. All right? So it turns out what we can show is that, one, our ideas of reachable events actually kind of respect some sort of linear structure, okay? So what we have is that if x naught, t naught is able to reach x1, comma t1, and if, let me call it z naught, t naught is able to reach z1, t1, then we have that for all scalars, alpha, beta, belonging to our field K, what we have is that alpha x naught plus beta z naught at time t naught is able to reach alpha x1 plus beta times z1 at time t1. Okay? So basically what we're saying is that if our system has a linear state transition map, then we can reach any linear combinations of states which we can ordinarily reach. Okay? All right, fantastic. So that's linearity. Now let's talk about time invariance. So what we're going to have for the time invariant property is that if we can reach, a state x1 at time t1 from x0 at time t0, then we could reach x1 at time t1 plus tau if we start at time t0 plus tau. All right, so this basically says that the states that we can reach don't depend on the actual objective times t0 and t1. Rather, they just sort of depend on the amount of time that's passed. Okay? All right, so I'll say if D is additionally time invariant, then I have for all tau in my time set t, x0, comma t0 being able to reach x1, comma t1 is in fact equivalent to saying x0, t0 plus tau is able to reach x1, t1 plus tau. Okay? So basically, if I can reach this event between times t0 and t1, then I can do the same thing if I just shift both of those by the same amount of time tau. Okay? All right, fantastic. So finally, what I'm going to say is something about a property called reachability. Okay, so far we've only talked about what it means for an event to be reachable. Now I want to declare a definition of reachability for an entire system. Okay, so finally we're going to talk about reachability. Okay, fantastic. So I'm just going to insert like a little definition into this theorem statement over here. So definition. So we say that D is reachable on the interval t0, t1, subset of t, if for all states x in my state space, I can go from the origin 0, t0 up until x, t1. Okay? So basically, reachability is kind of like a very specialized version of controllability, right? It just says instead of going from any start state to any end state between these times, what I can do is I can go from the origin to any end state between these times. Okay? So that's the definition of reachability. Now, what claim are we actually going to make about this? Well, it turns out for D, a system with a linear state transition map, right? Like we have kind of declared that we have in the statement of the proposition, I have that controllability on t0, t1 is actually equivalent to reachability on t0, t1. Okay? So even though it seems like reachability might be kind of a weaker condition than controllability, for a system with a linear state transition map, these two things are actually identically equivalent. Okay? All right, so I'm just going to give you a kind of quick proof sketch of this. So these first properties 1 and 2 are really things that follow directly from the definitions of linearity and time invariance. Okay? So 1 and 2, these are just basic applications of linearity and time invariance. Okay? So now I'm going to give you a more detailed proof of property 3, right? So property 3, what do we want to say? Well, one direction of this is a little bit straightforward, right? Do we have that controllability implies reachability? Well, yes, right? So controllability says that we can always go from x0, t0 to x1, t1, right? So all that we do is we just take x0 equals 0, and from there we conclude reachability. Okay? So that direction's pretty straightforward, right? So that's the forward direction. Now the reverse direction, what I want to show is that reachability implies controllability. Okay? So let's say, assume the system is reachable on the interval t0, t1. Now I want to show that it's controllable. Okay? So effectively what I want to show is that for all x0, x1, I'm able to reach from x0, t0, the final state x1, t1, right? This is the definition of controllability. Okay, so what am I going to do? Well, I'm going to fix some states, x0, x1, right? Then what am I going to do? Well, what do I know? Well, if I have reachability, then I can kind of get anywhere I want from the origin, right? So what I need to do is I'm going to kind of pick a very special state that I can reach from the origin, right? So by reachability, what I know is that I know from 0, t0, I can reach the special state x1 minus phi of t1, t0, x0, and 0 input, okay? And I can get there by time t1, all right? So what does this mean? Well, this means that there exists an input, u, right, which belongs to my input signal space, such that the following condition holds, such that phi of t1, t0, initial condition 0, and input signal u is equal to x1 minus phi of t1, t0, x0, and 0 input, right? This is just from the basic definition of what it means for an event to be reachable, right? Okay, so now what I'm going to do is I'm going to go ahead and bring this phi from the from the right-hand side over to the left. So what I get from there is phi of t1, t0, 0, u, plus phi of t1, t0, x0, 0 is equal to x1, right? Now, by applying linearity, I can actually combine these two things together, okay? So let's go ahead and apply linearity of the state transition map. What I get is that phi of t1, t0, now initial condition x0, and input signal u is equal to x1, okay? What we conclude from this is that x1 comma t1 is in fact reachable from x0 comma t0. Okay, this implies x0 t0 reaches x1 comma t1. Okay, so then we conclude that reachability does in fact imply controllability. Okay, that completes the proof. Okay, fantastic. So we have a couple of really important things over here that we've just kind of established. All right, so what we've shown is for an LTI system, what do we have? Well, first, what we have is that, it's sufficient to show reachability to conclude controllability. All right, so that was what we just proved, right? We can examine this easier, kind of less complicated problem of reachability if we want to make a conclusion about controllability of the overall system. Now, what else did we show? Well, this time invariant part of this result actually kind of gives us a way to simplify the choice of time interval that we're examining, right? So what we also find is it's sufficient to study controllability or reachability as its equivalent for linear systems on time intervals of the form 0, t. Okay? So the basic idea behind this is that if I show controllability on an interval t0, t1, for an LTI system, that's going to be the same as having controllability on 0, t1 minus t0. All right? And this is just because of that time shifting property. Basically, all that I'm doing is I'm shifting each of these times by a minus t1. By a minus t0. All right? And the time invariance property says that, our system has to respect this with respect to controllability. Okay, so with these two properties in mind, let's go ahead and see what we could say about the controllability of linear time invariant system representations. Okay? All right. Let's go ahead and outline this problem. So this is controllability of LTI system representations. Okay, so why are we kind of doing this? Well, let's kind of see what we did in the past, right? So in the past, if we take the example of stability, what we did first is we stated abstract definitions, right? And after we stated these abstract definitions, then second, we specialized to state space representations, okay? So for example, in stability, we studied some basic conditions for stability of x dot equals ax, okay? Once we did this, we were able to formulate sharp algebraic characterizations of our abstract properties. Okay, so in the past, we've kind of followed this pipeline of first start with a very abstract definition, then specialize to one of these concrete state space representations. And once we've done that, derive some very concrete, easy to check algebraic conditions that are both necessary and sufficient to show our abstract property. Okay, so now we want to do the same thing for controllability. Okay, the same thing for controllability. All right, so above, we've already done a little bit of work, right? We've kind of outlined this nice basic theorem that tells us if we have a very abstract LTI system, then we'll get these nice controllability and reachability properties, right? But these still aren't very algebraic properties, right? These are still things that are expressed in terms of these abstract state transition maps. So what we'd really like is tests for controllability or reachability that are simply as easy to check as something like an eigenvalue condition, right? That was super easy for stability, okay? If we could get something like that, that would be great, okay? So what we want is sharp algebraic characterizations of controllability. All right, so here what I'm going to do is I'm going to focus on, on the continuous time LTI state space representation. All right. And in particular, since in controllability, we're only really interested in the behavior of the state, we're just going to examine the state equation. All right. So our system is going to be of the form x dot of t equals a times x of t plus b times u of t. All right. So let's just go ahead and kind of analyze kind of a very basic plan of attack. So based off of what we said above, it's sufficient to analyze reachability on an interval 0, t to make conclusions about controllability on an arbitrary interval t0, t1, right? That's because this system does in fact have a linear and time invariant state transition map, okay? Okay, so with that said, let's kind of get started on this problem of determining nice conditions for controllability of these systems, okay? Or excuse me, reachability of these systems, rather. So what do we do? What to do? How to start? The eternal question. Well, what we can start out by doing is saying, okay, well, we know the basic problem is to get from the origin, 0, to, some other state at some time t, right? So let's fix a state that we want to get to. So fix a state x in Rn and a time t which is greater than 0, okay? So what I want to do is I want to solve for an input signal that gets me from the origin to x at time t greater than 0, okay? Let's solve for u such that I go from 0, 0, right? So 0 initial state, 0 initial time, and I get to x comma t, all right? This is really the problem that's at the heart of reachability, right? How do I find an input that gets me from 0 to a state where I want to be at a time that's given to me? Okay. So how are we going to do this? Well, let's just go ahead and start by examining the basic structure of the state equation, right? You might remember that based on the solutions to LTI systems, what we're kind of looking for is an input signal u that satisfies this equality, right? 0 to t, e to the a times t minus tau, b u of tau d tau, okay? This is just directly from the solution to a linear time invariant system. So how am I going to pick my input u? Well, there's a couple things that we could do, right? So let's try to pick u to really simplify the integral expression. Okay, so currently this expression is a little bit complex, right? U is kind of embedded inside that integral, and as a consequence of that, we can't just do any simple tricks like matrix inversion to kind of actually solve for what this input u needs to be, all right? So let's reduce the integral to a form where we can solve for u by matrix inversion. Okay, so what's our first step in doing this? Well, at the moment, for a general LTI system, this product right here, e to the a t minus tau times b, is not going to be a square matrix, right? So if what we're interested in is kind of getting some invertibility underneath us, then maybe we want to modify this thing to be kind of square or symmetric or some nice structure like this, okay? So what I'm going to do is, in order to kind of clean up this expression, I'm going to pick an input signal u of t equals b transpose e to the a transpose t minus t, okay? I'm going to multiply this by some matrix M, which I've yet to determine, and some fixed vector v, which I'm also yet to determine, okay? Now, if I plug this in, what are we going to get? I'm going to get that the above, 0t e to the a t minus tau times b. Now, if I plug in for u, I'll get b transpose e to the a transpose t minus t times m times v d tau. Oh, excuse me, this should be a tau. Okay? So right away, we have this nice symmetric structure in here. All right? So we've now got a kind of square matrix embedded in there. So let's go ahead and pull out m times v and then see what we could do. So 0t, sure, I'll get rid of these brackets. E to the a t minus tau, b transpose, e to the a transpose times t minus tau, d tau multiplied by mv. Okay? So what do I do now if I want to solve to kind of make this entire thing equal just to x, right? To this fixed x that I defined earlier. Well, what I can do is, now that this matrix is square, maybe it could be invertible, all right? Let's assume for a moment that it is. If this matrix is invertible, let's define m as the inverse of this, okay? And if we do this, then this expression is equal to m inverse times m times v, which is just equal to v, right? So then if I go ahead and I pick v equals x, then I should solve my problem. Okay? So what we've kind of sketched out here is if we pick this input of the form u of t equals b transpose, e to the a transpose, t minus t, now multiplied by m times x, right, where m inverse is this matrix that I highlighted up here, then it seems like we kind of get to our goal, all right? So this solves our reachability problem, all right? But this whole thing hinges on this special matrix m being invertible, right? If we don't have this, then this whole thing's going to kind of fall apart, all right? So what I'm going to do is I'm now going to define a special matrix that's equal to this thing in parentheses, right? Because this thing really seems to be central to our entire problem of controllability. All right, so let's go ahead and define that. It's going to be something called the controllability Gramian. So controllability Gramian. Okay, so what's the setup here? Well, we have a linear time invariant system, right? So I'll say, consider a linear time invariant system with state equation x dot of t equals ax of t plus b times u of t, right? So this system is kind of defined by this pair a and b. Now, what I'm going to do is I'm going to define the controllability Gramian. Gramian is the map WC, which goes from the non-negative reals into Rn by n, and it's defined WC at time t is equal to the integral from 0 up until time t of e to the a t, e to the a tau, b transpose, e to the a transpose tau, d tau. Okay? So, this might initially look a little bit different to what we had in the integral, but all that we've done here is actually just a little change of variables from what we had up there. Okay? So this is just a simple change of variables from the integral we found above. Okay? So our basic derivation above kind of leads us to believe, well, okay, if this thing is in fact invertible, then we should be able to solve our reachability problem, right? Because using this matrix or using its inverse, we can go ahead and kind of construct this input, right? Which is u of t equals b transpose e to the a transpose t minus t times wc of t inverse multiplied by x, right? Okay. Now it turns out that this thing is actually much, much more powerful than this, right? So it turns out this controllability Gramian isn't just sufficient for controllability, it's actually necessary for controllability as well, all right? So let's go ahead and state that as a theorem and kind of go ahead and prove this thing. Okay, the nice idea is controllability Gramian gives a sharp characterization of stability. Oh, not stability. Controllability. My gosh, what week are we in? All right, so let's state and prove this theorem. So theorem, this is the Gramian characterization of controllability. Okay, so what do we have? Well, let's say consider an LTI system with state equation x dot equals ax plus bu. Okay, same setup as before. Now I'm going to say that the following statements are equivalent. So statement 1, what I'm going to say is for all t greater than 0, my controllability Gramian WC of t is positive definite. Okay, so it's symmetric and all of its eigenvalues are strictly positive. All right. Now statement 2, what I'll have is for all t greater than 0, the system is reachable on 0, t. All right. Now my third statement, which I'll say is equivalent to these other two, is for all intervals t0, t1, subset R, the system is controllable on t0, t1. Okay? So let me just take a quick moment to kind of highlight what we're saying over here. We say that, if for all time we could show that our controllability Gramian is going to be positive definite, then that's equivalent to reachability for all possible time intervals 0, t, and that in turn is equivalent to controllability on any interval that we want. Okay? So this Gramian really gives us a sharp characterization of stability. All right? So I'm going to state a stronger version of this theorem a little bit later. First, we're going to go ahead and just prove this basic form. Okay, fantastic. So let's go ahead and get into this proof. So what I'm going to do is, if I want to show that 3 statements are equivalent, a nice thing to do is kind of prove like a little circle of implications. Okay? So what I'm going to do is I'm going to show 1 implies 2 implies 3, which then implies 1 again. All right? So first, let's show 1 implies 2. Okay, so let's say, suppose our controllability Gramian WC of t is positive definite. All right? Now what I want to show is that the system is reachable on 0, t. So I want to show it's reachable on 0, t for all t greater than 0. Okay? So let's go ahead and fix a time t greater than 0. And I want to show there exists an input u such that phi of t 0, 0 u equals some final state x. Okay? Oh, I also want to fix an x in Rn. Okay. So the nice thing is this is already kind of basically what we proved above, right? So these already proved above. What we showed is that if we pick this input signal u of t equals b transpose e to the a transpose times t minus t times wc of t inverse times your desired state x, then you go ahead and you get to this desired state x precisely at time t. Okay? All right. So we already, in fact, proved this result above. All right? We showed that this input gets the job done. All right. Great. So what about 2 implies 3? Well, what we want to show is that reachability on 0t implies controllability on t0, t1. Okay? But this as well, we've already pretty much showed, right? So we've already showed, or we kind of claimed above, I said that the proof was an application of time invariance. I showed, an application of linearity. So reachability on 0t, I said will imply controllability on 0t. Okay? Now what I want to show is that I have controllability on t0, t1. Okay? So I'll fix times t0 less than t1. So how are we going to conclude controllability on t0, t1? Well, we know you have reachability on our time set 0 t1 minus t naught. But based on time invariance, this implies that we have reachability on the time t naught comma t1, which then goes ahead and implies controllability on t naught comma t1. Okay, so that kind of concludes a quick proof of 2 implies 3. All right, so reachability on 0t for any time t that we want implies controllability on any interval that we want. Okay, all right, so finally let's go ahead and show that 3 implies 1. All right, so now we're going to assume that the system is controllable, and we want to show that its Gramian is positive definite. All right, so I'll say, suppose for all times t naught less than t1, the system is controllable on this interval t naught comma t1. What I want to show is that the Gramian WC of t is positive definite for all t greater than 0. Okay, so let's go ahead and show this by contradiction. All right, so I'll say assume for contradiction there exists a time t greater than 0 such that WC of t is not positive definite. All right, so something that's kind of a basic consequence of the structure of the Gramian is that WC of t is at least positive semi-definite. All right, so this is something you could verify if you just go ahead and take a look at the definition of the Gramian. So if we say WC of t is not positive definite, but we know that it's at least positive definite, this implies WC of t is singular, right? It's not invertible at time t. Okay, well, what does singular mean? Well, we know that there then exists a non-zero vector, v, such that we have 0 equals v transpose WC of t times v, all right? So we have a vector v that's in the null space of our Gramian. We're kind of hitting the Gramian on both sides of a v and v transpose, all right? So let's expand this definition. It's equal to v transpose integral from 0 to t, e to the a times tau, bb transpose e to the a tau, d tau times v. So let me go ahead and pull this in. Integral 0 to t, v transpose e to the a tau, bb transpose e to the a tau times v d tau. Now, what do I recognize in here? Well, I have that this and this are transposes of each other, right? So I could rewrite this as a 2 norm. So this is integral 0 up until time t of b transpose, oops, I'm missing a transpose up here, e to the a transpose tau times v 2 norm squared d tau, all right? Now the 2 norm is always going to be a positive quantity, right? So what does this imply? Well, what this implies is that if this whole thing is equal to 0, right, and I'm taking an integral over a non-negative quantity, then this term in here actually needs to be 0, right? And if this 2 norm squared is always equal to 0, then this thing inside here is always equal to 0, okay? So as a consequence, what I have is that b transpose e to the a transpose tau times v is equal to 0 for all time t, or tau, let's say, in 0 comma t, all right? Now, alternatively, I could just write this as the transpose, right? V transpose times e to the a tau times b equals 0. And this also holds for all tau in 0 comma t. Okay, so what happens? Well, what we're going to do now is we're going to kind of reach a contradiction by picking a very special initial condition, all right? So what do we have? Well, because the system is controllable on all time intervals, right? It's controllable on 0 comma t, all right? What this implies is that for any state x naught, right, starting at time 0, I can go ahead and I can reach the state 0 at time t, all right? I could do this for all x naught in Rn, all right? So as a result of this, there always exists an input, u and u, right? Such that I get 0 equals e to the at times x naught plus the integral from 0 to t e to the a times t minus tau b u of tau d tau. All right? So this is just the basic definition of a reachable event, right? I've just gone ahead and I've plugged it right into the formula for the state transition map of my linear time invariant system, okay? So what I'm going to do now is I'm going to go ahead and hit both sides of this with v transpose from the above, okay? So I'll multiply by v transpose. I can go ahead and pull this inside the integral. What I find is that since above we had v transpose e to the a tau b equals 0, this entire integral term is going to vanish, right? What I get is 0 equals v transpose e to the at times x naught, all right? So now what do we do? Now we pick a special initial condition. Let's pick x naught equals e to the minus at, right, the inverse of e to the at, multiplied by v. If we do this, what we find is that 0 equals v transpose e to the at, e to the minus at times v, and this cancels out and becomes the identity, right? We get 0 equals v transpose v, which we know is equivalent to v equals the 0 vector. But what did we say above? Well, we said v is non-zero, right? So we have v is non-zero, and all the way down here, we have v equals 0, okay? So this is a contradiction, all right? So what we conclude is that WC of t is positive definite for all times t greater than 0, all right? Okay, fantastic. So this completes our kind of little circle of implications over here, right? 1 to 2 to 3 to 1. That implies that all of these different things are in fact equivalent. Okay, so that's a proof. All right, so like I mentioned earlier, there's a couple of ways in which we can actually strengthen this result, right? So how can we actually do this? So strengthen the result. Well, some things that we could show, but don't have time for, unfortunately, in lecture, is that WC of t is greater than 0 for all t greater than 0, or excuse me, WC of t is positive definite for all time if and only if there exists a single time t naught greater than 0 at which WC of t naught is positive definite, okay? So the amazing fact is that it's actually sufficient just to produce one time at which our controllability Gramian is positive definite, okay? So one time for WC of t positive definite is sufficient to conclude positive definite for all time. All right? And a nice consequence of this is that what we have is that WC of t greater than 0 at a time t greater than 0 is in fact going to be equivalent to your system is controllable on any interval t0, t1. All right? So all that we need to do is just check a single condition, and then we get controllability on any interval out there. All right? Okay, fantastic. So this is a super strong condition, right? So what are some more kind of implications of this? Well, let's say there exists a time t greater than 0 such that WC of t is going to be positive definite, right? So let's just write out the definition, right? WC of t equals the integral from 0 up until time t, e to the a tau, b transpose, e to the a transpose tau, d tau, okay? So what does it mean for there to exist a single time greater than 0 such that we get positive definiteness? What does this condition actually depend on? What we see is that this only depends on A and B, right? This condition is entirely determined by my A and B matrices, okay? So it turns out that controllability for all time, just a property of A and B, okay? So this is not a property of my time interval T0, T1, Okay? If I'm controllable on one time interval, this Grommian test tells me that I'm actually going to be controllable on any time interval out there. All right? So what we have is that controllability exclusively depends on my A and B matrices. All right? For a linear time invariant state-space system, it actually has nothing to do with my interval. All right? So that leads us to make a definition of a controllable pair. And a controllable pair is, we say that AB is a controllable pair if A belongs to Rn by n, B belongs to Rn by m, and there exists a time t greater than 0 such that my Grommian WC of t will be positive definite. Okay? So this is in fact equivalent to saying my system is controllable for all intervals t0, t1. Okay? So a controllable pair is just a pair of an A and B matrix that results in a system that's always controllable, right? And because of this Grommian test, which says that we only need to exhibit a single time in which our system is controllable, this is just a property of A and B, right? So it kind of makes sense to talk about A and B being a controllable pair because they, both of them determine controllability for all times out there. Okay, nice. So let's continue. Where do we go from here? Well, there's a couple things that we kind of want to keep in mind, right? One of them is computability. So let's talk about computability. So one problem that we face is that the Grommian looks hard to compute. Okay? So what we'd like is some nice ways to really simplify computation of the Grommian. All right? So how are we going to simplify computation? Well, it turns out in one special case, there's actually a really nice and easy way that we could do this. Right? And this special case is where the A matrix of our system is stable, or Hurwitz. All right? So this leads us to the proposition, which is CTLE Grommian. All right? So let's say, consider a system with state equation x dot equals ax plus bu. All right? Now, if this matrix A is Hurwitz, then the infinite horizon controllability Grommian should define WC equals the limit as t goes to infinity, WC of t, which is also equal to this integral, 0 to infinity, e to the a tau, bb transpose, e to the a transpose tau, d tau, is given by the unique solution to the continuous time Lyapunov equation, A transpose P plus PA equals minus BB transpose. Okay? So this is a really powerful result. It says that the limiting case of this Grommian is actually, something that we're able to evaluate from this relatively simple matrix equation. All right? The proof of this is actually already immediate from what we did last week. Okay? So this is immediate from your CTLE solution formula. Okay? Because you might observe this term over here is actually nothing more than that same formula we derived last week for the continuous time Lyapunov equation. Okay? It's a nice one-line proof. Okay, very cool. So what you could show if you go ahead and do this is that, if WC, our infinite horizon Grommian, is greater than 0, then your system will be controllable. Okay. So this is good, right? This is kind of handy in the case where A is a stable matrix, but if A is not stable, right? If it's not Hurwitz, what can we do, right? So what to do if A is not Hurwitz? Okay, so the problem is that this Gramian is still hard to compute. All right. So what we're doing when we're trying to compute this Gramian is we're taking an integral of a product of matrix exponentials, right? With this BB transpose in the middle. That's something that's pretty hard to compute, right? Remember how much effort it took us just to compute a single matrix exponential all that while ago, right? So how do we actually go ahead and compute, something that tells us about controllability of our system in a much easier way, right? What we'd really like is a way to kind of get around this problem of Gramian. So the main problem that's making this Gramian really hard to compute is the matrix exponential, right? So we kind of define this by this series definition, right? Sum from k equals 0 up until infinity of a to the k over k factorial, right? Now, something that would really make our lives easier for computing these controllability conditions is if we were really able to kind of simplify this formula for the exponential, okay? What we want to do is we want to get an easier way to work with the exponential, okay? So you want to really study its algebraic properties, but not have to deal with this really messy infinite series that appears, okay? So what we can ideally do is we can just truncate the exponential to a few terms and not lose much information. Okay? So if instead of having to deal with this full infinite series, we could instead just look at a couple of terms of the matrix exponential and learn what we needed to learn for the sake of controllability. All right? This would make our lives so much easier. So it turns out there's actually a really nice theorem that lets us do this. Okay? And this is called the Cayley-Hamilton theorem. So let's go ahead and state and write a quick sketch of a proof for this theorem. Theorem, which is the Cayley-Hamilton. What this theorem effectively says is that if I go ahead and I plug any matrix into its own characteristic polynomial, I get the zero matrix back out. All right? So let's go ahead and state this precisely. So consider a matrix A. Sure, we could take it as complex, right? Cn by n. And let's suppose A has the characteristic polynomial, which remember is the polynomial whose roots are the eigenvalues of the matrix. Let's note it chi A of S, which remember is calculated determinant Si minus A, which equals, let's say, S to the n plus An minus 1, S to the n minus 1, all the way up until A naught, okay? Then A satisfies A to the n plus An minus 1, A to the n minus 1, plus A naught times the identity equals the zero matrix, all right? So this is super incredible if you think about it, right? If you take any matrix and you plug it into its own characteristic polynomial, as if that polynomial were a matrix polynomial, then you are guaranteed to get out the zero matrix, all right? This is super non-obvious, but it's a really amazing fact. And what this tells us is that the nth power of a matrix is going to be a linear combination of the first n minus 1 powers of the matrix, right? If we kind of inductively use this argument, what we could say is that really in the matrix exponential, all that we kind of care about is the first n minus 1 powers of A, right? Once we get past power n minus 1, we know from the Cayley-Hamilton theorem that we could express those powers as linear combinations of powers 0 up until n minus 1, okay? So that's what this theorem tells us. So Mark tells us all we need is powers 0 up until n minus 1, okay? So it's a super powerful theorem. All right, so let me go ahead and give a quick sketch of the proof of this. So I'm going to show you a nice proof that takes advantage of some of the structure of Jordan forms, okay? So first I'll prove it for a Jordan block. Then I'll prove it for a Jordan form. Then finally, I'll sketch the general case, all right? Which is really not too far off from the case of a full Jordan form. Okay, so first let's go ahead and let's prove this for a single Jordan block J. Okay, so consider a Jordan block, which I'll call J lambda equals lambda I plus n naught, right? Or remember, n naught is one of these nilpotent matrices of order n, right? It's a matrix which has zeros everywhere except in the first superdiagonal, where it's got ones just above the diagonal, okay? All right, so take a moment and think about what the characteristic polynomial of this matrix would be, all right? Let's say this is an n by n matrix, okay? Cn by n. All right, so I'll assume that you took a moment to think about that. Now, hopefully what you arrived at is that since the only eigenvalue of this matrix is lambda, and the characteristic polynomial is s minus lambda, or excuse me, all products of eigenvalue terms, right? What you can find is that the characteristic polynomial xj lambda of s is equal to the product s minus lambda to the power n, right? Okay, so if we were to go ahead and plug in our Jordan block into this expression, right, use a little bit of abusive notation and just pretend that, we can plug in a matrix into this expression. We have xj lambda of j lambda will equal to j lambda minus lambda times the identity, right? Where we replace this lambda term with lambda I, since we're now working with a matrix expression, right? This is to the power n, okay? So it should be a little bit lower. Okay, so if we go ahead and plug in the definition, we get lambda I plus n naught minus lambda I to the n, which equals n naught to the power n. Now remember, the multiplication rule for these n naughts says that up until power n minus 1, n naught to the k will equal some non-zero matrix. But once we hit power n, this matrix will actually be 0, right? Remember, this is exactly our multiplication rule for nilpotent matrices. Okay, so for the first case of this nice Jordan block, this result follows out pretty cleanly. Okay, so now for the next case, I'll say consider a matrix J in Jordan form. All right, so let's take J equals the block diagonal of J lambda 1 all the way up until, sure, let's call it J lambda k. All right, so let's say each J lambda I will belong to C mi by mi. All right, so now I want you to take another moment and kind of think about what the characteristic polynomial of this matrix would be. All right. Okay, so I'll assume that you gave that some thought. Now, hopefully what you arrived at here is characteristic polynomial of J will equal the product from I equals 1 up until k of s minus lambda k, or excuse me, s minus lambda I to the mi, right? We'll have products of factors which correspond to each of these eigenvalues and their multiplicities, right? Okay, so let's go ahead and plug in our matrix J into this. The nice thing is, since this is a block diagonal matrix, we'll actually get a really convenient structure, right? So chi j of j we'll show is actually equal to product I equals 1 up until k of j lambda 1 minus lambda I times I to the mi, all the way down until product I equals 1 to k, j lambda k minus lambda I to the power mi. Okay, so because this matrix is a block diagonal, applying a polynomial to this matrix is just the same thing as applying that polynomial to each of the blocks. All right? Okay, so we're going to have a block diagonal. There's going to be zeros everywhere else, right? These are 0 blocks of some appropriate size. Now, what can we say about this matrix? Is this matrix 0? Well, what we effectively showed above is that whenever we take the block, or we take the piece of this characteristic polynomial corresponding to that Jordan block, we get 0, okay? So on the lambda 1 factor, we'll have j lambda 1 minus lambda 1 times I to the m1 will equal 0 by our reasoning up there, okay? And since this is a product, if one of these factors equals 0, the whole thing equals 0, all right? So by applying that reasoning to each of these blocks, we get that this full thing is in fact equal to 0, all right? Now, the proof of the general case, if I take an arbitrary A in Cn by n, we know there exists a matrix T in Cn by n such that T inverse AT is in Jordan form. Now, there's a nice fact that the characteristic polynomials of A and J are in fact the same. Okay? So by applying this fact in conjunction with the previous fact, with the previous part, you can get the general case follows. Okay. And that concludes our proof. All right, fantastic. So the nice consequence of this result, right? Consequence is for any k greater than or equal to 0, you can express a to the k as a linear combination of identity a squared, all the way up until an minus 1, where n's the size of the matrix. Okay, this is something you could prove by induction. I'll include a proof of this in the notes. If you want to try it yourself, this is a kind of nice exercise to check your understanding. Okay? All right. So remember, our motivation behind this result was effectively to say, maybe we could really simplify our algebraic understanding of the matrix exponential by kind of truncating it, right? Now what we've shown is that really, to an extent, all that's relevant for some algebraic conditions is to just examine the first n minus 1 powers of A. All right? So let's go ahead and apply this result to controllability and see if we could get any simpler conditions than this, complicated, exponential integral thing that we have showing up in this controllability Gramian. Okay? All right. So let me go ahead and state a theorem, which is about something called the controllability matrix. All right? So it turns out we'll be able to get a super, super simple algebraic condition for us to check. All right? Let's go ahead and state this theorem. So let's consider a continuous time LTI system with state equation x dot equals ax plus bu, where a belongs to Rn by n. Then the following are equivalent. So we have point 1, which is going to be for all intervals t0, t1, which are a subset of R. The system is controllable on t0, t1. All right. Now we can also state this as AB is a controllable pair. Okay. Now, second, what we're going to say is the controllability matrix is going to be the matrix CAB equals BAB all the way up until AN minus 1B has full row rank. Okay? So, in other words, there is no vector V, which is non-zero, such that V transpose CAB equals 0. All right? So what this tells us is that controllability is actually as simple a condition as checking the rank of this nice matrix called the controllability matrix. Okay? All right. So this gives us our sharp algebraic characterization of controllability. This is really something that's as easy to check as like eigenvalues for stability, for example. Okay? So this is really nice and easy. All right. Let's go ahead and prove this result. So proof. So first, what I want to show is 1 implies 2, right? So I want to show that AB being a controllable pair implies that the controllability matrix has full row rank, okay? Now, let's just recall real quick. 1 is equivalent to my controllability Gramian being positive definite for all t greater than 0, right? So I'm just going to show that, 2 is in fact equivalent to this controllability Gramian condition. This is going to be a little bit easier for us to work with. Okay, so what I'll say is, suppose WC of t is positive definite for all t greater than 0. Now I want to show that CAB is full row rank. Okay, so let's kind of do this thing by contradiction, okay? So let's say, suppose for contradiction, CAB is not full row rank, all right? So what this means is that there exists a vector v, which is non-zero, such that v transpose times CAB is in fact equal to 0, all right? So if we write this condition out, we multiply v transpose by all these different controllability entries, get v transpose b, v transpose ab, all the way until v transpose a to the n minus 1 times b equals 0. What does this tell me? Well, this tells me that v transpose times a to the I times b equals 0 for all I equals 1, 0 through n minus 1. Okay, so if we now go ahead and we apply Cayley-Hamilton theorem, so Cayley-Hamilton, well, what does this tell us but v transpose x of at times b equals 0 for all t in R. All right? So let's see if we can now use this to get a contradiction. Well, we assume that our controllability Gramian is going to be greater than 0. All right? So what this means is that we should have v transpose WC of t times v is greater than 0, since v is a non-zero vector, right? But if we multiply this out, what do we get? V transpose integral from 0 to t of e to the a tau, b transpose e to the a transpose tau, d tau times v, 0t, v transpose e to the a tau, b transpose e to the a transpose tau, v d tau. But what we said above is that these terms are going to equal 0, right? What follows is that this entire matrix will equal 0, all right? So this equals 0. And what that is a contradiction, all right? Because we've essentially contradicted the fact that our Gramian is positive definite. Okay, so that concludes the first direction. Now let's show the other one. Now what I want to show is that 2 implies 1, all right? So let's say, suppose CAB is full row rank, okay? What I want to show is that my Gramian will be positive definite. So I want to show WC of t is positive definite for all t greater than 0, because this is equivalent to my system being controllable, right? Or AB being a controllable pair, okay? All right, so let's do this by contradiction again. So let's suppose for contradiction, there exists a time t greater than 0, such that WC of t is not positive definite. All right, now remember, since we always have that WC of t is at least positive semi-definite, this is equivalent to saying WC of t is singular. Okay, so it's not invertible. What this means is that there exists a vector v, which is non-zero, such that v transpose WC times t times v equals 0. If we go ahead and we perform a little bit of computation, right, we could show that this is equivalent to the integral from 0 to t of v transpose, b transpose e to the a transpose tau times v 2 norm squared d tau being equal to 0, right? We just go ahead and plug in this matrix. And based on our same reasoning above, what this implies is that b transpose e to the a transpose times t times v equals 0 for all t in 0t, which is the same thing as v transpose e to the at times the b equals 0 for all t in 0, t. All right? So if this is true, what we could do is go ahead and differentiate with respect to t, okay? And as a consequence of taking the first n minus 1 derivatives, what we'll find is that if we evaluate at time t equals 0, we end up with the condition v transpose times a to the I times b equals 0 for all I and 0 up until n minus 1. Okay? What does this mean? But v transpose times CAB equals 0. All right? This lands us up at another contradiction. All right. So from this, we effectively conclude that controllability and this controllability matrix having full row rank are indeed the same thing. Okay, fantastic. So what we've just shown is that this controllability matrix, so let's state some remarks. Controllability matrix gives a complete and easy characterization of controllability. Okay? As long as this matrix is full rank, we're guaranteed to have the A comma B as a controllable pair for our system. All right? What are some problems with this condition? So problem is that rank of CAB being full is a yes or no condition for controllability. Okay? So the problem is that since we have a yes or no condition for controllability, this controllability matrix really tells me nothing about how easy or hard my system is to control, right? So if, for example, I write out the system 0, 1, minus 1, minus 1 times x plus 0, 1 times u, controllability matrix says it's controllable, okay? I just go ahead and make that check, right? It'll tell me, yes, that system's controllable, right? But now, if I replace this with, say, 10 to the minus 7, the controllability matrix will still tell me that the system is controllable, right? But I'm going to have to put in a huge amount of effort if I actually want to do anything, okay? System is really hard to control, okay? So this yes or no test really doesn't give us a lot of granularity, okay? So this is where the Grommian comes in. So the Grommian, harder to compute, but tells us more, okay? The basic idea is, since the Grommian is a nice square matrix, right? And what we're interested in is its singularity, right, or its lack of singularity. If we just examine essentially what its minimum singular value is, this gives us a measure of how hard our system is to control, okay? Because effectively what this minimum singular value tells us is how close our Grommian is to being singular, right? If it's super close to 0, then that means our Grommian is basically singular, right? So if we have a really, really small minimum singular value, what that means is we'll have a situation like this, right? Where our system is going to be really hard to control, okay? So controllability matrix gives us an easy test, but it's a yes or no test, all right? On the other hand, the Grommian, it's harder to compute, but it carries much, much more information, and it actually tells us a degree of controllability, all right? How easy or hard our system is to control. Okay. So with that said, let's go ahead and give a very, very brief treatment of agenda item 3, which is this controllability decomposition, okay? The basic idea of the controllability decomposition is, sometimes it's actually going to be okay if our system is not completely controllable, right? So sometimes might be okay if not controllable, okay? So if, for example, I take the system x dot equals 1, 0, 0, minus 1 times x plus 1, 0 times u, then I can't control this piece of the state, right? So this is not controllable. But if my aim is to, say, stabilize this system, the nice thing is this is already stable, right? So the basic idea is if the part of my system that I can't control is already stable, maybe that's going to be fine for some purposes, okay? So in this example, it's really kind of clear which part is stable and which part is not stable, or which part's controllable and which part is not. But in general, that's not going to be so clear, right? So what we need to do is we need to kind of actually decompose our system to a state where it's going to be clear which part is controllable and which part is not controllable. Then once we've done that decomposition, we can check, okay, is our uncontrollable part stable? If so, maybe that'll be fine, all right? So let's kind of set up the basic structure for how we do this. So first I'm going to define something called the controllable subspace. All right. So I'm going to state one of a number of equivalent definitions. Sometimes this is also called the reachable subspace of the system. Okay. So I'll say consider the LTI system x dot equals ax plus bu. Now, the controllable subspace is the space, which is just the range of my controllability matrix, CAB. Okay? Now, again, this is one of a number of equivalent definitions. There are other ones that, kind of lend more of an interpretation in terms of reachability, but just for the sake of time, I'm going to state this nice and easy definition. Okay? So what I want to do now is I want to kind of split my space up into a couple of different pieces, right? I want to split it up into the controllable subspace, which, as the name kind of suggests, is something where I'll have control. And I want to split it up into that and an uncontrollable subspace, something where I have no authority whatsoever. And in order to make this transformation, to make this decomposition of my system, there's a couple properties that I need to check, okay? So the first one is that my controllable subspace, range of CAB, is A invariant, okay? So what this means is if I go ahead and I take something in my controllable subspace and I multiply it by A, then that remains in my controllable subspace, all right? So let's go ahead and prove this real quick. This is kind of just a minor technical result that'll be useful to making our general decomposition, okay? So I'll say, suppose V belongs to the range of CAB. Then, what does this mean? Well, this means there exist vectors V0 through Vn minus 1, such that V is equal to the identity times V0 plus A times V1. Oh, hold on. That's not quite right. B times V0. There we go. That's better. Plus AB times V1 plus all the way until A to the n minus 1 times B times Vn minus 1. Okay? What I want to show is that A times V still belongs to my space. So AV is equal to AB V0 plus A squared B times V1 plus A to the n times B Vn minus 1. Now, what do I do? Well, I want to show that this kind of still has this form up here, right, where I can write it as some sort of linear combination of vectors times these different pieces of my controllability matrix, right? But this only goes up to power n minus 1, right? In this new expression, well, I have a power n all of a sudden. So what do I do? But I apply Cayley-Hamilton theorem, okay? So this lets me express A to the n as some powers alpha naught times the identity plus alpha n minus 1, A to the n minus 1. And from there, we can conclude that A times V will still belong to the range of my controllability matrix CAB, okay? So I do a couple of simplifications, and I see that, okay, I could still express it as linear combinations of these A to the I times B, where I goes up to power n minus 1, okay? All right. So with this said, let's go ahead and state our final result, okay? It's going to be theorem, which I'll call controllability decomposition. Okay. So what I'm going to do now is I'm going to use this controllable subspace and this proposition, which we just proved, to split up my space into a part which we can control and a part which we cannot control. All right? Okay. So let's say consider an LTI system with state equation x dot equals ax plus bu, where now the dimension of the range of CAB is equal to some r, which is less than or equal to n. Okay? Then there exists an invertible matrix T, which belongs to Rn by n, such that I have T inverse AT is of the form AC hat 0, A12 hat, A uncontrollable hat, T inverse times B equals B controllable hat 0. Okay? And this satisfies A controllable hat belongs to R by R. B controllable hat belongs to R by M. And A controllable hat, B controllable hat, is a controllable pair. Okay? So basically what's going on here is I've split my system into two different components. Okay? So what's happened, we split our system into a controllable part. So this is this A controllable hat, B controllable hat part, and an uncontrollable part. And this corresponds to A uncontrollable hat, and then just 0 for my inputs, right? So we could basically see this entire bottom layer, right, has no inputs appearing. So it's super clear that, we won't actually be able to access anything down there. Well, this top layer, right, has a control input appearing, right? What's more, AC hat and BC hat is a controllable pair, okay? So we've gone ahead and we've split our system into a controllable part and an uncontrollable part, right? Just to give you a really quick sketch of how this transformation is created, what you do is you first pick a basis, basis V1 VR for your controllable subspace, okay? And then you pick a basis VR plus 1 all the way through Vn for its orthogonal complement, okay? Range CAB perp. Then what you do is you take your matrix T to be V1 through Vn, and you could show that T inverse AT and T inverse B have the desired form, okay? Now you could show that your controllable piece, A controllable hat, B controllable hat, is controllable by evaluating the controllability matrix, okay? And you'll find that you do, in fact, get the desired structure. Okay. So what I just mentioned a little while ago is that, if this uncontrollable piece of our system is already stable, maybe that's going to be fine for some purposes, right? So this leads us to a definition called stabilizability, all right? So definition, which is kind of like a weaker form of controllability. Stabilizability. Okay, so basically what this happens, or what this says, is that, if we take this decomposition of our system above and we examine this matrix A uncontrollable, and that matrix turns out to be stable, or Hurwitz, then the system is stabilizable. Okay? So if this part that we have no control over is already stable, then we declare our system to be stabilizable. All right? Now I just want to state one final theorem about how you can go ahead and check for stabilizability I'm not going to prove this theorem. I'm just going to kind of tell you what it is. This is called the PBH test for stabilizability. Okay, so I'll say that a pair AB is going to be stabilizable if and only if the rank of the matrix A minus lambda I B is equal to n. This needs to hold for all lambda in C such that the real part of lambda is greater than or equal to 0. Okay? So basically what we're doing is we're going ahead and we're scanning across all values of lambda which are unstable. And if we get a rank drop in this special matrix over here, then that means that we're not going to be stabilizable, right? But instead, if for all unstable values of lambda, our rank remains constant, then we do have stabilizability, okay? All right, so I'll go ahead and leave it off here. Thanks for watching.